Okay, so here we're given the information about this cobalt NH3, 6, 3+, and I'm going to tell you that this is a strong field case. Let's draw the electron configuration for this complex ion. Let's draw the electron configuration for this complex ion. Okay, so you found the oxidation numbers. Here's our oxidation numbers. We know from our previous work last time that the ammonias have 0 charge. So if this is going to be +3 overall, that has to all be coming from the cobalt. Now cobalt has 9 valence electrons, neutral cobalt.
So it's going to be 6 then? It's going to be 2.
9 minus 3 is 6. Good. And we know this is in the strong field case, so we put these in 1, 2, 3. Now where should I put the 4th electron in the strong field case? Down below. Because this is too big of a leap to get up here. This is just the normal case that you would have done before we'd gone over this material. You would assume that these would all fill up before we would start putting these in here. Okay. So the next one goes down here because this is too big of a price to pay. How do I know this is a strong field? Because in this problem we were just told it's strong field.
It just slipped out of my mind. A little bit of practice.
Okay. Yes. So actually, yeah, on this problem I think that you confused the strong field and the weak field case.
I just didn't do it.
And on the last problem, I think that you confused the strong field and the weak field. So it seems like that's a very easy mistake to make, right? So you want to double check yourself here, because that's what this whole topic is about, distinguishing between the two cases. Okay. Now, question is then, is this compound paramagnetic or diamagnetic?
This is a diamagnetic because it's paired up.
They're all paired up. That's right. It's good that you got that memorized. Diamagnetic. So that might have been the problem here. The problem might have been, if you're told that this is strong field, is it paramagnetic or diamagnetic? So those are kind of the two types of problems that you might see. Some problems might ask you whether something is paramagnetic or diamagnetic. Some problems might ask you whether it's strong field or weak field, like the previous problem that we did. Some problems might tell you that it's strong field or weak field and ask you something else, like whether it's para or diamagnetic. This means that this would be weakly repelled by a magnetic field.
And then could it also tell us that it's diamagnetic, and then we'd have to figure out which one for strong field or weak field?
That's an excellent point. I could easily have given you this the other way. I could have told you this is diamagnetic and asked you if it's strong field or weak field, and then you would have to draw it both ways, and you would see that only one of them comes out diamagnetic.
Yeah.
Okay, good. Now let's do this one. Let's figure out whether this is paramagnetic or diamagnetic. Now this compound, I'm going to tell you this is a weak field compound. I'm going to tell you this is a weak field compound, and the question is this complex paramagnetic or diamagnetic? And in this case, we're just told that this is a weak field.
It's 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1
Looks like you went through the right process. First, we find the oxidation number. Well, fluorine we can figure out its charge from the periodic table. Since it's next to last column, each of these wants to pick up 1 electron, so that would be -6 total. This has to be +3, so that 3 minus 6 gets -3. So we're really in the same situation as before, I think. We can use the word before. There's 6 valence electrons. 1, 2, 3. And now, because this is only a small price to pay in energy, we'd rather go up a little bit in energy than pair up the electrons. 1, 2, 3, 4, 5. Only now are we forced to put the 6th down here. And you both figured out correctly, this is the paramagnetic case because there's unpaired electrons. All you need is 1 unpaired electron. So we have more than enough unpaired electrons for this to be paramagnetic. You can see that both of these were about the same oxidation number of cobalt. And then therefore this demonstrates to us that whether you have strong field or weak field can definitely make the difference between whether you're diamagnetic or paramagnetic.
Yeah.
So again, the problem could have been done the other way. They could have told us that this was paramagnetic and asked if it was strong field or weak field. And then we could draw both of these pictures and see that only one of them is consistent with being paramagnetic. Good. All right, well, both of you went through that fine. No mistakes, so that's good. Okay, now, how do you know, again, whether a ligand is going to give us the strong field or the weak field? Well, there's something that's called the Spectrochemical Series. Notice that in the Spectrochemical Series, the elements that are on the left are the ones that tend to be strong field, and the ones on the right tend to be weak field. And it's hard to predict the ones in the middle. Well, it depends. I don't think your instructor would expect you to have these memorized. I think if necessary, you would be given this information.
Yeah, he actually said that in class.
Okay.
Be given.
Okay, yeah. So you just have to know how to interpret it.
Mm-hmm.
All right. Now, I'm using my textbook. I didn't see this in your textbook, but I think I do remember seeing it in your lecture notes.
Yeah.
So you can go back to your lecture notes to see the spectrochemical series that your instructor wants you to know. I think your textbook left this out, but in your lecture notes there should be something like this.
Mm-hmm.
But like I say, you don't have to have it memorized. So, would cyanide tend to be the strong or the weak field?
Strong field.
Right? And how about, say, bromide?
Weak.
Yeah, the ones in the middle are harder to predict. Let's see if that's consistent with what we have here. Here we had 2 examples with cobalt with the same oxidation number, one with ammonia and one with fluoride.
Mm-hmm.
So what would the spectrochemical series predict about fluoride?
That it would be weak field.
It's towards the right. So we tend to think that maybe it's going to be weak field.
Yeah.
And how about ammonia?
It's more towards the strong field. So.
Yeah, it's a little bit in the middle, so maybe it's not always going to be strong field, but who's more likely to be strong field? The ammonia rather than the fluoride, and that certainly was consistent with our results.